Hi. The last class I talked about microbial kinetics. I also discussed about the first order kinetics. I hope you all remember this simple equation. All it states is like imagine you take a bioreactor, you add some substrate and then give some stirring, you supply some oxygen. Just assume this is an aerobic reaction, and then you add some microorganisms. So you all know microorganisms are going to consume your substrate, which means your substrate is going to decrease with respect to time, while your microorganism concentration is going to increase with respect to time. Yeah. And what we saw is like this expression is really good if you are in the exponential region, say time versus microbial concentration. So it will be something like this. Yeah, if you are in the exponential phase, if your microorganisms are growing in the exponential phase, then you can use this type of expression. This is a simple first order expression that will allows you to calculate a property of your microorganism that will explain how fast some number is replicating per unit time inside the reactor. Yeah, so this is the I call it as a specific growth rate. So what these parameters says are it explains how your microorganisms are growing at one particular experimental condition. Say you start your experiment from a substrate concentration of 100 grams per liter, and then you started your experiment with the inoculum concentration of say 1 grams per liter, and you perform the experiment and then you just monitor how your microorganisms are growing with respect to time. Yeah, so imagine these are your experimental data, and this data can be represented by this type of equations, and then you can get your specific growth rate, which has a unit of 1 by time. But imagine if you start your experiment with a different substrate concentration. Say you started your experiment from 25 grams per liter, 50 grams per liter, 100 grams per liter. For some reason, microorganisms, how fast the microorganisms replicate, they change. They change with respect to your initial concentration. This is not a hypothesis. This is an experimental fact. Many people did a lot of experiment, and they found something like this is happening. Yeah, say you have time here, and you have your microbial concentration here expressed in grams per liter. Say your time is expressed in hours, and you take some reactor, you start with say some 25 grams per liter, your substrate concentration. Yeah, and then it will take some pattern like this. And if you start for the same experiment with 50 grams per liter, same seed mass or inoculum concentration, you will get a completely different trend. It will still retain this exponential trend like this, but how fast, if you look at here, if I draw a curve here, line here, so you see your microbial concentration is slightly lower and your microbial concentration is slightly higher. So what it states is like the rate of replication of your microorganisms or cells per unit time is faster when you increase your initial substrate concentration. It's so amazing how microorganisms work. Yeah, like if their capacity to consume food and product is not same. Yeah, it changes with how much inoculum how much seed concentration you supply. Yeah, so sorry, how much substrate concentration, initial substrate concentration, which is inside the reactor. It's if you start with a small lower in substrate concentration, your the growth rate is lower. If you start with a higher substrate concentration, the growth rate is really not high but slightly higher than the one if you perform the same experiment with a slightly lower initial concentration of your substrate. I hope I did explain correctly. And if you perform another experiment at 100 grams per liter, your rate is going to increase, yeah? And then you do another experiment at 150 grams per liter, it's going to increase. So let's write it here. Your initial substrate concentration, 50 grams per liter, say S0 is equal to 100 grams per liter. Here you say 200 grams per liter, and then say S0 is equal to 250 grams per liter, and after some stage it becomes constant, yeah? It won't increase by a lot, yeah? So imagine you put S0 300 grams per liter, that growth when you start the experiment with 200 grams per liter, or when you start your experiment with 300 grams per liter. See, let me put different color. Say these red circles are your microbial concentration when you start with an initial substrate concentration of 300 grams per liter, and the blue lines here, just assume they are the microbial concentration when you started your experiment with 200 grams per liter. So this is like a different set of experiments you perform with the same microorganism, same reactor volume, same inoculum concentration. The only difference is your substrate concentration, yeah? Or you can call it as nutrient concentration, which will be consumed by your microorganism and convert your reactants into products. And again here, just go back to the same equation which is here, this one. So you can apply the same law for each of these experiments here. So imagine you take x versus t, S0 is equal to 50 grams per liter, and from here you can calculate your specific growth rate, mu value, using that simple expression I showed you before, mu t, or you can use the monod expression, ln of x2 minus ln of x1 by t2 minus t1. So you can pick any 2 points here, and you can call this as x1 and you can call this as x2. You draw some line, this will be t2 and this will be t1, and then you apply this formula, the monod formula, and that from there you can get your specific growth rate, yeah? So and you can repeat the procedure for the next experiment. Say you have time versus microbial concentration. This time you started your experiment with 100 grams per liter. You can apply the same rule, x2 minus ln of x1 by t2 minus t1, and then pick any 2 points, yeah? So this will be your x2, this will be your x1, and then just from there you can get t2, t1, and then apply this equation. So what we are going to do is, like, you perform a lot of experiments for different substrate concentration, and then you calculate your specific growth rate, say, like using this monod expression. And then if you observe the data, say you started from 25 grams per liter, 50 grams per liter, 100 grams, 150, 200, 250, 300. So you perform a wide range of experiment, yeah? Starting from different initial substrate concentration. This, say, 1 by r, the unit of your specific growth rate. I don't know the number, so it will be some number, yeah? Some number which refers to number of cell divisions happening per unit r, or in 1 hour, sorry. And what happens if you like to plot this one, if you want to know the trend, sir, your substrate concentration versus your specific growth rate, you can plot them. If you have data, why not to plot? So you put your substrate concentration here, grams per liter, and you put your specific growth rate here, which is 1 by r, or any time 1 by minute or 1 by second, how you express the time, that matters, yeah? So And then if you plot, if you imagine if you have an experimental data, if you plot it here, you will get some trend like this for most of the microorganisms. You'll get something like that. So what it says, what this trend, this is an experimental fact. If we have facilities to do this experiment, then we can try it and we can plot. You will get something like that. Yeah. So what it says is like once you, if you see here at this point, this mu value, your specific growth rate value, remains constant, and it reaches a maximum. Yeah, so there is a maximum in this curve. So you can call that as mu max. So this is the maximum specific growth rate that you can attain. Yeah. So and then if you want a relationship between mu, like how your specific growth rate changes as a function of your substrate, something like you need some mathematical function. If you need a mathematical function that can relate how your specific growth rate changes with respect to your substrate concentration, you need to develop something. Yeah. So the simplest one without any constant is something like this. So we need a function. F is a function which is a function of your substrate concentration that can relate, that can predict your specific growth rate. So we don't have to develop such an equation, yeah, because Jacques Monod, he's the Nobel laureate. He came up with some very elegant empirical expression. Yeah? He believes for most of the microorganisms, if you even after you performed a lot of experiments starting with different substrate concentration, and then you get this type of data. Say I showed in this graph, you started with the different substrate concentration, and then you get mu value from here using the Monod formula. Then, and if you plot them, it's going to be, sorry, you're going to get a trend, and this trend can be mathematically represented using a simple formula. Yeah. So this is the equation of Jacques Monod. So this is what he gave, and this is your y, sorry, this is your specific growth rate, and these two are your substrate concentration, and this is your maximum specific growth rate. If you plot the data of mu versus substrate, like the one I showed here, this one, you can already see here what is your mu max. So that's your maximum specific growth rate in this curve. So what about this one, Ks value, constant? This is called Monod constant. This one is, I already said, this is called maximum specific growth rate. Yeah. So what is this Ks value? It's like we can calculate what's the significance of this Ks value. So I just want to make you sure that this expression was just proposed by Jacques Monod only to explain this type of growth behavior. Yeah, there is no physical or theoretical assumptions behind these expressions. All he need is one simple function that can relate your specific growth rate versus and with your substrate concentration. Though this equation is completely empirical, we can get some level of theoretical meaning for this one. One way to do is take this equation and then put mu is equal to mu m by 2. So what is this? This means just assume your specific growth rate is exactly equal to the maximum specific growth rate, which you see here, mu max, maybe different color. This maximum specific growth rate which you observe here, we call it as mu max, and we're just going to say, you know this mu max value, and we're going to divide it by 2, so which means that this is like half of your maximum specific growth rate. Yeah? And we are going to assume your specific growth rate of your microorganism is equal to this maximum specific growth rate by 2. Just give some equation number 2, and this you give one expression like for monod expression we can give equation 1. So we are going to substitute in equation 2 in equation 1. Say like mu is equal to mu max s ks plus s. So we are going to replace this with mu, the maximum specific growth rate, by 2. So you can use mu m or mu max, it's up to you. Both means maximum specific growth rate. Ks plus s, both will get cancelled, so you will get s is equal to 2 ks plus 2s. You just, oh sorry, no, it will be the other way around. Ks plus s is equal, k suffix s, this one will be equal to 2 multiplied by s, yes. So ks will be equal to 2s minus s will be equal to s. So what it states, ks is something which will be equal to your substrate concentration when your specific growth rate reaches half of your maximum specific growth rate. So that's the whole meaning. So this is what we derived. Yeah. So what we did is like we assumed your specific growth rate is exactly half of your maximum specific growth rate. So that's what we did here. So something like that, and when we solve, this is what we get. Your substrate Ks will be equal to your substrate concentration when your mu will be equal to mu max 2. So so this is the theoretical meaning of this Ks value, or K, the monod kinetic constant. So the monod kinetic or monod constant Ks refers to the substrate concentration at which the specific growth rate of the microorganisms reaches exactly half of the maximum specific growth rate. So which means you know the unit. So ks is equal to your substrate concentration, so which means the unit of ks is grams per liter. If you express your substrate concentration in grams per liter, so ks will be expressed in grams per liter, and your mu max, this is equal to your specific growth rate, or maximum specific growth rate. So the unit should be equal to the unit of your specific growth rate. So if your mu max is if your specific growth rate is expressed in, say, in 1 by r or 1 by second, then your mu max should be expressed in terms of 1 by r or 1 by second. So same units. Yeah? So the beauty of this equation is it will allows you to to correlate a wide range of experiments, yeah, while like how do you call, it allows you to correlate the growth property, exactly the growth property of your cells in different as a function of substrate, different substrate concentration, yeah, like you can use this simple equation, but this will help you to correlate your time with your microbial concentration at one experimental condition. But if you look at this expression, you can get mu at different substrate concentration, and then you can correlate them. So which means this equation is really helpful if you are performing a lot of experiment, and especially if you want to study the effect of your initial substrate concentration on the specific growth rate, then this equation becomes very handy, yeah? So I'm going to solve one problem, and oh sorry, there is one more limiting condition of this equation. Imagine, just to take this graph, yeah, we can go through the graphical thing. Time, specific growth rate, say it grows like this, say this is your mu max, just assumes this happens at say 10 1 by r, yeah? So exactly half of that is 5 1 by r. You can draw some line here, and then if you come down, oh sorry, this is your substrate concentration, yes, expressed in grams per liter. So whatever this value here, so this is equal to your substrate concentration when this mu value is equal to mu max by 2. So the substrate concentration at which this happens, that will be equal to your Ks. So this will be equal to your Ks. So this is the way, this is graphical method. If this is a graphical method to calculate the monod constant Ks, yeah? Or if you want to know the substrate concentration at which your specific growth rate will be equal to half of your maximum specific growth rate, so you can take a graph sheet and draw this graph and try to interpret, you know, where is your maximum specific growth rate, which is here, and then you divide it by half, and you come to that particular point, draw some line here, and then come down, and then you can calculate your Ks value. So this is the whole point, yeah? So and just imagine if you are doing some experiment at very high concentration, say somewhere around here, say this Ks value happens at 1 grams per liter, just for example, and you want to start your some experiment, say at 20 grams per liter, yeah? So obviously this is going to be constant, so you will have your maximum specific growth rate here, yeah, because this is going to be constant. After some time, after some level of substrate concentration, the effect of substrate concentration have no effect on your specific growth rate of your microorganisms. So we can, this is an experimental phenomena, but we can test this, whether this experimental phenomena is valid while we are using your monod equation, yeah? So we know the monod expression is mu max substrate Ks plus substrate, yeah? So I said to you, this value, which is this particular value 20 grams per liter, yeah? This particular value 20 grams per liter, and you come back here, this is 1 grams per liter, this is your Ks value. So what is this if you compare these two values? So what this experimental condition, what it says is like when your substrate concentration yes is very high, very high, very higher than the your Ks value, which is here. Your S is very higher than the your Ks value here, moment constant. Sorry, somebody was knocking my office. Yeah? Imagine S is very higher than the Ks value. Just go back to this graph. So I hope you all are following this one, because this is not a difficult thing to understand. So you have 20 grams per liter. Say you have only 1 grams per liter here. So obviously 20 grams per liter is very higher than 1 grams per liter. So you just call your substrate concentration S is equal to 20 grams per liter is much higher than your Ks value, which is only 1 grams per liter. And we are saying that this is a here you have the number 1 gram per liter and 20 gram per liter, but we are going to use the parameters to explain that. So just assume you come back here, you can state that in words your substrate concentration is much higher than the Ks value. Yeah. See, when we are going to test some experimental condition. So what is going to happen, or what my monod expression is going to predict when my substrate concentration is much higher than this Ks value. This Ks value itself is a substrate concentration when your specific growth rates reach half of its maximum. Yeah, so just stop. I'm going to call this as equation 3. So we have this equation here. So we can substitute. So when S is, imagine here, just imagine S is 20 grams per liter and Ks value say is 0.1 grams per liter. So what is this like? If you take S plus Ks, that will be equal to 20.1, approximately equal to 20 grams per liter. So which means S plus Ks is equal to S. Yeah. When S is much higher than Ks value. So when Ks is negligibly small when you compare with your S value, then this condition, you can write that mathematically in this way. So you say this one as 4. So substitute 4 in the monod equation. So mu max Ks, S plus Ks. So this is equal to mu max K suffix S divided by just there is something. Okay, I wrote this one wrong here. This is your substrate concentration, mu max multiplied by S. I hope I didn't do this mistake before. No. Mu max by S, so this will become S. Just get cancelled, so mu will be equal to mu max. So this is, so one thing you can just you can confirm from this expression is like your monod expression, this one, it actually predicts your experimental observation. When if you perform a lot of experiment at higher substrate concentration, your mu is going to be mu max. Yeah? Especially if you perform at a substrate concentration which is much higher than your Ks value here, then your mu will be equal to mu max, which means monod expression is really a good expression. At least it predicts some experimental observation. Though Monod proposed this equation as completely empirical without making any assumptions on anything, he just think if I have a data of a specific growth rate and substrate, it's going to follow some rule and it, or some pattern, and that pattern can be represented by this equation. So this is one of the limiting conditions of your monod kinetic constant. Sorry, monod kinetic monod sorry monod expression. This is so confusing. So if in the exam, if I ask about like explain monod expression and its limiting conditions, you have to write the monod expression and then you have to solve two of its limiting conditions. One is like when your growth rate is equal to half of its maximum specific growth rate, then your your substrate concentration will be equal to Ks. And then the second condition is the one just now I showed you. When your substrate concentration is much higher than the Ks value, K suffix s value, or higher than monod constant, then your specific growth rate will be equal to the maximum specific growth rate of the microorganisms. So these are the two limiting conditions of the monod expression. So this is really a cool expression, and it has only two constants. So I'm going to solve one problem now for you, and we are going to use this particular equation, and then you will understand how it's really an useful expression. So imagine I'm going to say some example. Just imagine we performed some experiment. Say we used glucose as a substrate. We are going to express them in grams per liter, and say some microorganisms, some name, maybe, I don't know how to pronounce this one, Cerevisiae. So in fact they use this one to convert your glucose into some alcohol. So this is your microorganism. So the beauty of this the monod expression is we really don't have to care what is the name of the microorganisms. All you need to care is the pattern, like how they grow. If they grow exponentially, you can get your specific growth rate, and from that specific growth rate you can try to relate how they grow as a function of your substrate concentration using that monod expression. So monod gave a lot of expressions, empirical expressions relevant to your microbial kinetics, and that's what we are covering, especially in this last 3 or 4 lectures, I think, lecture 4, lecture 5, and then I also solved a few more problems, and probably I need one more lecture to cover some more topics related to microbial kinetics. So this is really an interesting topic to read, and you must know this before we are going to learn enzyme kinetics, which I'm going to cover in lecture 6. So coming back to this problem, so we are going to take some glucose, we're going to use some microorganism, and then we're going to convert them into some products. But for the moment we have some data related to your substrate concentration, say grams per liter. Just assume we already say time versus x, so different substrate concentration, say you start from say 0.51 grams per liter, and say 1 grams per liter, 1.7 grams per liter, 2.5 grams per liter, and so on, and you calculated the specific growth rate, and we are trying to, and we have the data of your substrate concentration and your specific growth rate expressed in terms of 1 by r. So these are the data we get from the lab. So what it says, like when your substrate concentration is 0.5, your specific growth rate is equal to 0.06 divisions per hour. Yeah, when your substrate concentration is equal to 1 grams per liter, your specific growth rate is 0.1 cell divisions per hour. Yeah? This is a unit of numbers per hour. And now we need to calculate. I'm going to ask you to calculate the maximum specific growth rate of this microorganism. Calculate the maximum specific growth rate and the growth and the concentration at which your specific growth rate reaches half of the maximum specific growth rate. Yeah? Normally when you do some experiment and when we calculate the specific growth rate versus you won't get a nice smooth curve like this. Yeah? So we will get somewhere here and there some bit of fluctuations. Yeah? So that's why we need, that's why we cannot go always for the graphical method. Imagine I can easily plot this value, your specific growth rate value here and your substrate concentration here, and then I can plot. I can take your maximum specific growth rate here, and then I can take half of that number, and then I can come back here and then I can calculate your substrate concentration. Yeah, so if you know this is your mu max by 2, so we can draw one line here. So if this is your mu max by 2, you draw one line here and then you come down here. So this will be equal to your Ks value. But the experimental reality is like you won't get a smooth curve like that. Yeah? So if you perform some experiment and you calculate after a laborious process, no, it's really a laborious process too. You have to do several experiments and then you will get a graph like this, time versus x, and then from each you have to study individually each of those graphs to get your specific growth rate. From there you go to this type of graph. Yeah? And you will have a lot of fluctuations. So when you have this type of fluctuation, how are you going to get exactly your mu max value? So it's a bit tricky process. Yeah? And then you have to come here, and so that's why we need some curve fitting technique, and that's when, where is that equation? It's not in this page. So that's why we need this type of equations. So I hope you all can follow this one. Yeah? It's not really tough. So we are going to calculate. So in the problem, all I ask you to calculate is your maximum specific growth rate and your Ks value. So how to calculate this parameter? Yeah? You know mu m by Ks plus S. So what we are going to do is we take the inverse of this one on both sides. This will be equal to 1 by mu Ks by mu ms plus substrate by mu ms. So substrate and substrate gets cancelled, so you will end up with a linear equation Ks plus mu ms plus 1 by mu m. So and then you want, you can write more easy way so that you can understand. So what it looks, this is equal to y is equal to mx plus c. This is a linear equation, yeah. So your x will be equal to 1 by s, your y will be equal to 1 by y, and your slope value m will be equal to ks by mu m, and your intercept will be equal to 1 by mu m, yeah. So we can get this value and this value by plotting. Say you plot, this is your y, 1 by mu, you plot them in the y-axis, and 1 by s, this is your x value, so 1 by s, you plot it here, you will get something like that. You must get, and then you take a line, you will get a linear relationship between 1 by mu versus 1 by s. So what we did is like we took a non-linear relation, you see substrate and mu, you have a non-linear relationship between your specific growth rate with your substrate. We made them into like a linear type relation, 1 by specific growth rate and 1 by substrate. There exists a linear relationship between these two values, yeah. So we altered the x and y axis for comfort. So all you are going to do is like, I gave you the substrate value grams per liter. I gave you your microbial concentration x grams per liter. So we are going to apply this linear equation, 1 by mu is equal to so we are going to plot this in x and plot this in y axis. So for let's calculate these values first. It's 0.5, 1, 1.7, 2.5, 6, 9, 12, 15, 16. I know it's a bit time consuming to teach this way, but I think it's not a bad idea to go a bit slow like this. Then you are going to take inverse of substrate concentration. Sorry, this is your specific growth rate expressed in terms of 1 by r. So 1 by mu, so your unit will be equal to hours. 1 by your specific growth rate, so 1 by your substrate concentration is 1.588. I already calculated this using Excel, so I'm just going to write it here. Zero 0.65 and then 16.67, 8.33, 5.56, 4.54, and then 3.33, 3.125, 3.03, 2.94, and 2.94. So I just took inverse of your specific growth rate, and then I took inverse of your substrate concentration. So what we are going to do is like we are going to plot these two values, these two columns, sorry. So what I'm going to plot is like, I'm going to plot 1 by my specific growth rate and 1 by my substrate concentration. I need to get some linear curve like that. I can try to plot. I don't have graph sheet, so I will create my own. In the exam, you have to use a graph sheet. Yeah, don't do like this. This is a really horribly bad idea. So in the exam, you must use a graph sheet. If not, your answers will be really bad. It won't be accurate. You can use graph sheets or you can use Excel sheet, whichever is comfortable to you. And then say we can plot 0.5, say 1, 1.5, and then 2. So what are these first values? Like 0.5 is 0.0, sorry, 2 is 16.7. No, this, let me redo this. I think I should be careful with. So this value should say like 2, 4, 6, 8, 10, 12, 14, say 16. We have the maximum value in x is around around 16, I think. Yes. No, I think this one is correct. We are plotting 1 by substrate concentration and 1 by specific growth rate. In the table I see maximum is 16 point, so y value should have 16, that's correct. And our substrate concentration maximum is 2, so this has a value of 2, that's correct. Yeah. So you can plot them now. So so what is this value? When you have value of 2, you have something around, I'm going to use a different color, value is around 16.6, and then when you have 1, it's around 8.33, somewhere here, and then when you have 0.58 is 5.5, somewhere around here, 5.5, and then when you have 0.4, it's around 4.5, see, somewhere around here, and then 0.3 is 0.16, somewhere around when it's 0.1, it's 3.125, somewhere around here. Most of these values are somewhere around here, and if you take a linear line, you will get an equation y is equal to mx plus c, or it will be exactly y is equal to 6.9527x plus 2.1482. If you go back to this equation here, I know I'm going very slow, but it's not a bad idea. So your slope value should be equal to Ks by mu m, and your intercept is equal to 1 by mu m. Yeah? So this will be equal to your intercept 2.1482. So therefore your maximum specific growth rate will be equal to 1 by 2.1482, 1 by r's, and then so what will be this number? Let me calculate. This is equal to, so your mu max or maximum specific growth rate is 0.465, 1 by r's. In the exam, if there is, if you forget to write your units, I'm not going to give the marks. Yeah, so I'm not going to mention this in the exam question paper. You should remember yourself. Yeah, there is no value for any of this number 0.465. If there is no unit, there is no meaning for that. Yeah, this 0.465 can be 1 by minute, 1 by seconds, and it has a different meaning. So I mean different magnitude. So you must include your units. So that's how you get your mu max. And you go back here, this is your slope value, Ks by, that's your slope value, which is here 6.9527. So Ks will be equal to 6.9527 multiplied by your maximum specific growth rate. So that will be equal to Ks is equal to 6.9527 multiplied by 0.465. So what will be this number? Let me calculate. 6.9527, yeah. So that will be equal to, Ks will be equal to 3.236 grams per liter, because your substrate concentration is expressed in grams per liter. So that's why your Ks value, we are going to express them in grams per liter, yeah. So I think you solved the whole problem. So what is this number like? It says like, for this particular system, glucose and whatever the microorganism, your maximum specific growth rate will reach its half of its value when your substrate concentration will be equal to 3.236 grams per liter. So that's the whole meaning of this one, yeah. So if I'm going to ask what's your substrate concentration when your maximum specific growth rate is going to reach 1/4 of the maximum, when your specific growth rate is going to be, or is will be equal to 1/4 of the maximum specific growth rate, yes. So I can, why not, yeah? If you max by 4, so when this will happen, if I ask some question like that, you should be able to calculate it in the final exam. So you can do that only if you have some understanding about this simple equation. Yeah, so this is really a simple, very simple expression. It has only two constants, and you can linearize them like the one I showed here, this expression. So it's really easy to apply, and it allows you to calculate the monod constants and your maximum specific growth rate, which is a property of the cell. So I'm going to stop the lecture now. I will upload it soon, and probably in the next lecture I will try to solve one or two problems related to microbial kinetics, and or maybe I will go directly to enzyme kinetics, and then we can solve few more problems connected to microbial kinetics and enzyme kinetics together. Because once I finish enzyme kinetics, I want you to make sure that you are going to use same type of equations like monod equation. In enzyme kinetics, we are going to use exactly similar mathematical structure, that some equation which has exactly same mathematical structure of a monod expression. We are going to, that expression is called Michaelis and Menten expression, but it has completely different meaning. The constant Ks in enzyme kinetics, it has a different unit, and also the mu max value, the maximum specific growth rate which we saw in kinetic constant, that has completely different unit when you are going to deal with enzyme kinetics. So I think it's better in the next lecture I teach enzyme kinetics, and then we do two different problems, one related to microbial kinetics, one related to enzyme kinetics. Then you will have some level of understanding like what's the key difference, especially when our key difference I mean in terms of the units of the different parameters involved in this, in the different mathematical expression that's used to explain the microbial kinetics and the enzyme kinetics. Yeah? Enzyme kinetics are slightly is more difficult, yeah, more difficult to treat mathematically than microbial kinetics, because in enzyme kinetics we are going to discuss a lot of things, not only how your substrate is getting converted into products. We are also going to see some other effects like a competition effects. They are really tough to deal with but they're really tough to deal using mathematical expressions, but still we are going to do that by, but just just want mm, to realize that it's not going to be easy. Enzyme kinetics, yeah. Math. I think I'm going to stop the recording now. Thanks for listening, and if you have any doubts you can ask me, you can call me in Teams. I prefer if you call me and ask me some doubts, you know, it, at least I will understand where you have the problems. At the moment I really don't know whether all of you can follow the lectures, or I don't know whether you find this simple or you find this very tough. So you must, I prefer you to contact me through Teams, or if you're not feeling comfortable you can just write an email. Thank you so much.